Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on basic control systems for mechanical engineers. So, today we are going to study about root locus. So, we'll take a simple control system. So, this is a negative feedback loop, and here we have the reference R of S, and there is the feedback portion. This is the controller D of S, the plant G of S, and based on this we get Y of S. In addition, we have at the feedback portion, we have the sensor dynamics denoted as H of S. So, we can write down this Y of S divided by R of S as basically D of S into G of S divided by 1 plus D of S G of S into H of S. So, as you can see here, it's about the numerator consists of multiplying the open loop part, and the denominator is 1 plus the open loop part into the feedback path. So, in this equation transfer function, we can find the characteristic equation. So, the characteristic equation basically is the roots of which are the poles. We are interested in that from, as we discussed in the previous lectures. One is stability, second is the performance, because poles predominantly decide our response. So, we go D of S into H of S, G of S is equal to 0. Now, what we can do is we can take this particular portion here entire and denote it as equal to K L of S. So, basically this turns down into K L of S, where L of S is some transfer function and K is a kind of a gain, or we can call it a parameter, which we are going to vary, and as it varies we are going to study how the pole locations change, and that is the basic concept of root locus. So, we can denote this L of S to be of something of the form B of S divided by A of S, where B and A are polynomials in S, and we'll, as I mentioned, we'll plot roots for different values of K. So, these roots are basically of 1 plus K L of S is equal to 0. Now, we can take this transfer function, basically L of S, and since it's B of S by A of S, this can be expressed as multiplication of the M zeros divided by multiplication of the N zeros, N poles, and basically N is greater than or equal to M. So, for example, if we take 1 plus K L of S is equal to 0, that implies if we substitute instead of L B by A, we will have 1 plus K B of S divided by A of S is equal to 0, which can turn out to be A of S plus K B of S is equal to 0. Now, if we consider this particular the left hand side here, this basically denotes a polynomial which is equated to 0, and say there are n roots basically, because the highest degree of this will be n, that is the order of a. So the highest power will be s to the power n. So we'll get s and so on till s r minus n, where r I are roots of a of s plus k b of s is equal to 0. So as we have discussed so far, that we are going to vary k, and for that we are going to find what is the roots, or basically the poles of this closed loop system as we vary k. So we'll start with a simple example. So let us take an example where this open loop characteristic is L of s divided by 1 divided by s into s plus 1. So in this case, b of s will be equal to 1, a of s is equal to s into s plus 1. So now if we go backwards, we are interested in finding the roots of a of s plus k into b of s. So that is basically, if we substitute, we will get s square plus s plus k is equal to 0. So we are interested in finding the roots of this particular equation. Now in this scenario, this is a simple quadratic equation in s. So we can write down the roots are 1, 2 as basically minus half plus or minus square root of 1 minus 4k divided by 2. So in this we get the roots, both the roots of this particular equation. Now let us vary k, and in general in root locus what we do is we consider that k is greater than or equal to 0. So let us start what happens as we increase k. So you will see that is k is varied from 0 to 1 by 4. The roots are real and lie between -1 and 0. The second case is when this particular discriminant part is equal to 0, that is k is equal to 1 by 4. So in this case we get two real roots at minus half, and when this discriminant part turns out to be negative, that is k is greater than 1 by 4, the roots are complex with real part minus half. So here we have identified what happens under different values of k, and now what we are going to do is we are going to plot the root locus based on this. So what we do is we draw the S plane, real and imaginary axis. Now we start, so let us draw the two poles of this L of s. So the first one will be at s is equal to 0. The first one will be at s is equal to 0. The second one will be at s is equal to -1. And what you will see is as we go on increasing the value of k, so the location of k when k is equal to 0, the poles lie at the poles of this L of s. Now as we increase the value of k, you will see that this particular path, the root here starts moving on this real axis. Similarly, from the other side it starts moving this axis, and at exactly at minus 1 by 2, when k is equal to 1 by 4, they will be both at minus 1 by 2. Now, as the value increases, one of the roots will go in this direction and the other root will come in this direction. Here we are not much interested about which direction it goes, but in general just giving a rough sketch. So, you will see that the roots of this closed loop system start from the poles of L of S, that is 0 and minus 1, then they come to this symmetrically come to minus 1 by 2, and from there they start deviating out of the real axis and go on to infinity. Now, what can we say about the stability of this system? So, at k is equal to 0, it is marginally stable because there is one pole at s is equal to 0. For k greater than 0, it will be always stable because this the two roots lie in the left half plane. Here we have considered one example. Now let us move and look at another example. So let us say in this particular case that our D of S, that is controller and sensor dynamics, are set to 1, and we have G of S which is of the form 1 divided by S into S plus C, and here C is our basically our parameter. So, if we look at the characteristic equation, what you will see that it is 1 divided by S into S plus C plus 1 is equal to 0. So, this can be rearranged to get as S square plus CS plus 1 is equal to 0. So, from this equation, the equation we have seen previously is 1 plus k into L of S is equal to 0. So, based on that, if we do a comparison, we can identify that k is equal to C and L of S is basically equal to S divided by S square plus 1. In this scenario, then B of S is equal to S and A of S is equal to S square plus 1. And we can find the roots R12 for this particular equation as minus C by 2 plus or minus square root of C square minus 4 divided by 2. So, based on this, by varying the values of C, we can get a plot the root locus. So, for example, say this is our S plane, and for L of S we have the two poles here and 1 0 here. So, for C is equal to basically 0, what you will find that it will be plus or minus j, which are basically the pole locations. And as you vary C, it will vary along this particular circle. So one part will look something this form, the other part, as you can see, will be symmetric, and as we go on increasing, you can find that one of them will go to this. So it will look something like this. This is more or less a rough sketch. So this represents the root locus. But the two cases we have discussed so far, if you see the equations, they are basically just quadratic equations which can be easily solved. We do not have a very perfect method so far if the degree of the polynomial increases, and so we need some guidelines to plot the root locus for general cases. Okay, so as I said, we need some guidelines to find the root locus. So the root locus of L of S is the set of points in the S plane where the phase of L of S is 180 degrees. So what do we mean by that? So let us consider L of S divided by L of S is basically B of S divided by A of S, right? And as we had seen in earlier, we can express this as S minus Z1, S minus Z2 into S minus Zm. Similarly, in the denominator, we have S minus P1, S minus P2 and so on till S minus Pn. So now if we consider any particular portion, like say for example, we just consider S minus Z1. So here this S is a complex number, will have certain magnitude and phase. Similarly, Z1 will have certain magnitude and phase. So if we want to find the phase of L of S, what we do is we want to find the phase of L of S. We take the phase of S minus Z1 plus phase of S minus Z2. We add this all up to S minus Zm, and then for the remainder, when we come to the denominator, that is the poles, we do a subtraction. So in this manner we can get the phase, and let us denote for zeros, for example for this particular 0, that the phase here is some phi 1, for this 0 phi 2, basically it's psi m. So we start with psi 1, psi 2 and psi m. So basically for zeros it's psi I. Similarly, when we have the poles, we consider some phase phi 1, phi 2 all the way up to phi n. So basically for poles we have phi I. So if we now insert this into this formula, we will get summation of all psi I minus summation of all phi I. So this represents the phase of L of S. And what this statement here says is the root locus is the set of points in the S-plane where the phase is 180 degrees. So basically it's the set of all points which satisfy this condition, that is the phase of L of S is basically equal to 180 degrees plus 360 degrees into L minus 1. So what we do is, say we are given a particular system and we want to, so for example what we do is we create a pole 0 map in the S plane. So here in this case, say we have, for this system there is one pole here, then there is another pole here, and we have two poles here, and we have a 0 here. Now say we want to find the set of all points. What we'll do is we'll take one point in an arbitrary point in the S plane and say denote this as S0, and from that what we'll do is we'll draw lines to the poles and the zeros. So basically for the poles, so for example this angle will be say phi 1. Similarly we have this angle phi 2 which is equal to 0 because they are in a straight line. Similarly here we have phi 3 and here we have phi 4. And this angle from the 0 is psi 1. So we vary this S0 to cover this entire plane, but finding this measuring phase at each point is cumbersome. Basically cumbersome. So in this case we need a better method or better guidelines. So as we have discussed through this example, we need better guidelines. So we are going to study next some of the rules for plotting the root locus. So the first one is, of a root locus there are n branches of poles of L of S as k is varied. These n branches start at poles. So and m of them end at zeros, because basically there are only m zeros of L of S, and remaining go to infinity. So if we consider the equation, this is what we had discussed a while ago. So now if I insert k is equal to 0, this translates to the equation A of S is equal to 0. And A of S are basically the poles of the open loop transfer function L of S. Now if I take k to be infinity, in this scenario B of S is equal to 0 is the one of the cases which which implies that we are going to end at zeros of L of S. Another scenario is if we have this equation, we can write L of S is equal to minus 1 by k, right? And if k now tends to infinity, then basically this L of S also should tend to infinity, and this is strictly under the assumption that n is greater than m, because if n is equal to m, what happens is all branches which start at the poles of L of S will act at all zeros of L of S. So when there are more branches, because there are more poles than zeros, some branches will follow this particular equation, and if k tends to infinity, then L of S has also to tend to infinity, in which case, since the number the order of the denominator is greater, that is the power of S is greater, if S tends to infinity, then L of S will follow this particular equation, and similar it will this left hand side will be equal to 0 and the right hand side will be also equal to 0. So in that case it is satisfied. So in this case, when k tends to infinity, either B of S is equal to 0 or S tends to infinity. So basically here we will have m branches ending at zeros and n minus m branches going to infinity. The second rule is that the loci on the real axis are to the left of an odd number of poles and zeros. We'll in a while come to examples about this, but the whole idea is you plot the pole 0 map, and the only part of the real axis is the part which is to the left of an odd number of poles and zeros. This will be clear from the extensive number of examples we will be discussing after we complete all these rules. The third rule is for large values of k, n minus m loci are asymptotic to lines at angles phi I radiating from S is equal to alpha on real axis. So basically this phi L is 180 degrees plus 360 degrees L minus 1 divided by n minus m, that is the branches which remain, and L is equal goes from 1 to all the way up to n minus m. So this is the angles which the branches which remain, which we have seen here, that is the difference between number of poles and number of zeros. They move in an asymptotic fashion for large values of k, and these are the angles, and these asymptotes radiate from this S is equal to alpha on the real axis, and this is the formula for alpha. So basically summation of all pole locations minus summation of all zero locations divided by n minus m. The fourth point is a loci will never intersect with itself. So for example, let us consider in the S plane, say we have, there is one pole here, 1 0 here, then this will go in this fashion. So say this is one case. Now we consider the same S in the same S plane, the same system. So you have one pole 1 0, and say I have given some root loci which looks like this, root locus. So basically what you will see is this is the correct one and this is the wrong one, because here the loci is intersecting with itself, and that is never going to happen. Next we come on to the fifth rule, that is complex conjugate poles have paths that are mirrored over real axis, and finally on the real axis loci always enter and exit at 90 degrees. So the angle between the loci and the real axis is always going to be 90 degrees. So here we have discussed 6 rules. These are sufficient for creating a rough sketch and designing controllers. There are other rules and more details, but I believe we are not going to cover those up because these are sufficient. And the second aspect is, if you want an exact, this is sufficient to just create a rough sketch. For an exact representation, what you can do is you can use in MATLAB something, a command called Locus of the system. So you can define the system in the transfer function form and you can plot the root locus. Now next we are going to discuss some examples on how the to understand how these rules are applied and to get root locus for different kinds of systems. Okay, so now we have discussed these different rules. So how we'll see now how we can apply these rules. So let us start from the examples we have already done and see whether we get the same result. So let us consider this example, the first one which we discussed here, where L of S was 1 divided by S into S plus 1. So here we can plot. First we start with the S plane, and next what we do is we create a pole 0 map of this system. So here we will have S is equal to 0, S is equal to minus 1. Now looking at, if you see the first rule, what we can say that there are poles at 0 and minus 1, and there are no zeros in this particular system. So from the first rule we get that there will be n branches, n in this case is equal to 2. So we have 2 branches which start at poles. So the first one will start from 0, the other one will start from minus 1, and both end at s tends to infinity, because there are no zeros. Now that is the first part. Let's come to the second rule, which says that the loci on the real axis are to the left of an odd number of poles and zeros. So if we consider the real part, the positive real part, what you will see that there are no poles and zeros on the right hand side. So this cannot be part of the root loci. Now if we come to between 0 and -1, what you will see is on the right side you will see that there is one pole. So that means this particular segment will be a part of the root loci. So what we can do is this particular segment between 0 and -1 is a part of the root loci. Now if we come beyond -1, there are even number of poles, which implies that this part won't be a part of the root loci. So we understand now that the only part in the real axis, for the real axis, root loci lie between 0 and -1. The next part is understanding. In this case we have n minus m is equal to 2. So there will be asymptotes. So we first find what is the value of alpha. So we get alpha, which is summation of all pole locations, which in this case is -1, minus summation of all 0 locations, which in this case is 0, divided by n minus m is equal to 2. We can similarly get phi 1 by directly inputting this formula. We know n minus m is equal to 2, so we will have L is equal to 1 and 2. So if we substitute 1, we get 180 degrees divided by 2, which is 90 degrees, and phi 2 to be 270 degrees. So that means a part of the root, the asymptote will something be of this form. So say this is minus half, this is 90 degrees, this is minus 270 degrees, and this location is minus half. So our root loci will lie according to this. So we have applied these rules. Now based on this we will plot the root loci. So let us say first it starts from here and then proceeds. The other one starts from here and proceeds this way. And basically the angle here where it leaves this real axis, as we have seen, is according to rule 90 degrees. So if we go back, you will see that we get a similar result from these rules for root locus and the way we solved this quadratic equation. So both the quadratic equation method as well as the rules which have been prescribed give the same solution. Now let us look at this second example. So in this case, L of s is equal to s divided by s square plus 1. So what we will first do is we will plot the s plane, real imaginary axis, and as we had done in the last case, we will plot a pole 0 map. So this 0 is at s is equal to 0 and these poles are s is equal to plus or minus j. Now we will apply, so basically poles at plus or minus j, 0 at s is equal to 0. So here we have two branches, right, because the number of poles is equal to 2. So they start at plus or minus j, one ends at S is equal to 0, other goes to S tends to infinity. Now coming to the part of locating, the third rule mentioned that how we can, the second rule mentioned that how we can, what part lies on the real axis. So if we see this, if we look at the positive part of the real axis, there are no poles or zeros on the right hand side. So this this part does not come within the root loci. Whereas if we look at the negative part of the real axis, you will have three, the number of poles and zeros, if we sum them up, is equal to 3, which is an odd number. So in that case, the loci will cover entire negative real axis. So this entire part along this entire axis is basically covered. The next rule is, as we have seen here, the value of n minus m is equal to 1. So that means there will be an asymptote. So if we look at this asymptote, the value of alpha will be the summation of all poles and zeros. So summation of poles yields the value is equal to 0. The summation of zeros is also 0. So in that case, alpha will be 0. And this phi 1 will be basically n minus m is equal to 1. So we will have 180 degrees plus 180 degrees plus 0 divided by 1. So in that case, it will be 180 degrees. So in this case, the asymptote will be basically, if we plot, something like this. So 180 degrees means the negative real axis. So now we can plot the root loci. So we start from the poles and we come to the real axis. It enters the real axis at a 90 degrees angle and we need it to be symmetric. So basically this part are symmetric. Now one of them goes to the 0, other goes to infinity along the asymptote. Now in this sketch, what we have not determined which of them goes to the 0 or which of them goes to the pole, say the one coming from plus j or minus j, because we are trying to get just a rough sketch for the purpose of our control design. For more details, as I had mentioned, we can always plot it using computer based software such as MATLAB. So this is the pole 0 case, and this is the same for the, even for when we did it using the quadratic equation, we got the same result. So the quadratic equation and these rules for root loci we have discussed give us the same result. So now we will discuss another example. So we will come to another example where L of S is basically 1 divided by S into S plus 4 the whole square plus 16. So if we draw the S plane, first thing what we will do is make a pole 0 map. So in this case, there are just 3 poles. Basically at 0, minus 4 plus or minus 4j. So here we have 0. So this will be one here and the other pole will be here. And there are no zeros. Now coming to the next rule about locating the part on the real axis, which is on this root loci. So what you will see is, if we consider the positive part, there are no poles or zeros on the right part. So what we can say is this part does not come within the root loci. Now if we consider next part, that is between this -4 and 0, what you will see is this part has an odd number of poles on the right side. So basically what we can say is this part lies along the lies within the root loci. So the root loci will lie on this part of the real axis. Similarly, if we come beyond -4, what you can see that there are 3 poles. So again an odd number. So that means this entire negative real axis is spanned by the root loci. So loci covers negative real axis. Now in this scenario we have n minus m equal to 3. Because there are no zeros, all the 3 branches will go to infinity. So in that case, what we need to find what is alpha, phi 1, phi 2 and phi 3. So alpha in this case will be minus 8 by 3. Phi 1 will be 60 degrees, phi 2 will be 180 degrees and phi 3 will be 300 degrees. So we are going to get an asymptote which starts at this particular location. So I say this minus 8 by 3 denotes minus 2.67. So it will start from here at 60 degrees, then 180 degrees and 300 degrees. So this is how this should be more like 60 degrees. That, but this will be more. So now if we are going to plot the root loci, and this will be, so the first part of the first root loci will be directly going here, which is 180 degrees. So the one at s is equal to 0 will move towards along 180 degrees. Then the other one from here will start this way and will follow this asymptote. Similarly, the one on this side will follow this asymptote at 300 degrees. So we get this root loci for this particular system. So this root locus, basically the reason why this pole starting from s is equal to 0 went again at minus 180 degrees is because we had to satisfy this rule where that the complex conjugate poles have paths that are mirrored over the real axis. So as you can see, both this path here and this path will be mirrored with respect to each other. So this way we can get a rough sketch of the root locus for this particular system. So now we'll see another example where L of S is equal to S plus 5 divided by S plus 2 into S plus 4 into S plus 8 into S plus 9. So for this system we are going to plot the S plane, and we are going to focus next on doing a PZ map. So here we have at -2, -4, then we have a 0 at -5, then another pole at -8, another pole at -9. So basically there are 4 poles and 1 0. So basically there will be 4 branches. One starts, one of them will start from a pole and end at a 0. Remaining will start from poles but go to infinity. Now consider what happens on the loci on real axis. So if we see this real axis, the positive part is out of question since there are no poles or 0. When we come between, again same applies to between S is equal to 0 and -2. Now between -2, so say this is -2, this is -4, -5, -8 and -9. So when between -2 and -4, what you will see is there is an odd number of poles on the other side, so on the right side. So basically this part, this segment is a part of the root loci. So basically the part between -4 and -2. Now between -4 and -5 there are an even number of poles and zeros on the other side. So we are not going to consider that. Now next when we come to the other side of -5, that is between -8 and -5, what you will see that the number of poles and zeros are basically an odd number. So we will consider that part. So between -8 and -5. I can rather say -4 to -2 and -8 to -5. Similarly, between -9 and -8, there are 4, the number of poles and zeros combined is 4 on the right hand side. So that does not cover, become a part of our root loci. And beyond -9, if we sum up the number of poles and zeros, they are 5. So an odd number basically. So what we are going to do is till infinity, this part is there. So we can say going from infinity to -9. So these are the 3 regions of the root loci within this particular part. With on the real axis. So now we are going to start with the next part is there will be the value of n minus m is equal to 3. So there will be 3 asymptotes and alpha is basically equal to -6, and the 3 asymptotes are phi 1 is equal to 60 degrees, phi 2 is equal to 180 degrees and phi 3 is equal to 300 degrees. So starting from -6, you will have this asymptotes. So now let us start. So if we look at -9, our first root loci starting from the pole -9 will go to infinity along 180 degrees. Then the other one, that is at -8, this one will directly go to the, sorry, this one will directly go along to this particular 0. The next one, which starts at -2 here and will follow asymptotes. So let us say we consider 60 degrees, and the one on -4 will start from minus asymptote, and these both branches will be. So we have for this system, and this is what it looks like. We have studied root loci. We started with a simple quadratic. Do this root loci using face of L of S, but that was, both these methods were quite rules for root loci. Studied the guidelines which already exist for root loci. Considered a number of examples. Now in the next class, what we are going to do, root loci and how we can use knowledge of root loci, and with that I'd like to conclude today's.